Welcome to Measuring an Equilibrium Constant, the Scatchard Plot. If we want to measure an equilibrium constant, then we measure concentrations, really activities, of the involved species at equilibrium. Now we're going to examine how spectrophotometry can help us with this task. Suppose we have an equilibrium where we have P reacting with X to give us some complex Px. And if we ignore activity coefficients, then we can say that the equilibrium constant K is equal to the concentration of our products, Px in this case, divided by the concentrations of our reactants, P and X, raised to the powers of their coefficients in our balanced chemical equation. In this case, all the powers are 1 because the coefficients are all 1. Suppose we keep the total amount of P constant and prepare a series of solutions that contain various increments of X. So the total concentration of P in all forms, P and Px, is P naught and is given by this equation. So we have P naught is equal to the sum of the concentrations of P and concentration Px. We can then solve this equation for the concentration of P. So the concentration of P is equal to P naught minus concentration of Px. So let's rearrange the equilibrium expression here from K equals concentration of Px over concentration of P times concentration of X to concentration of Px over X is equal to our equilibrium constant K times the concentration of P. And now we can replace the concentration of P. So now we have our equilibrium constant K times the quantity P naught minus Px. And now if we plot concentration of Px divided by X concentration as a function of Px concentration, then we get a line with slope of negative K, the opposite of the equilibrium constant. And this type of plot is called a Scatchard plot that we have over here. If we know the concentration of Px, then we can find the concentration of X via the mass balance. So we know X naught is equal to the total X concentration. Well, that has to be the concentration of Px plus the concentration of X, the unbound X. We can use spectrophotometric absorbance then to find Px. Suppose that at wavelength lambda, P and Px have non-zero absorbance and X has zero absorbance. And let's set the cell path length B to 1.000 centimeters, so we can omit it from Beer's law. The absorbance then is equal to the absorbance is equal to the molar absorptivity of Px times the concentration of Px plus the molar absorptivity of P times the concentration of P. Note that we can ignore the concentration of X because X is not absorbing. The molar absorptivity of X is 0 at this wavelength. We can then substitute concentration of P is equal to P naught minus concentration of Px. And that means that we have the absorbance is equal to the molar absorptivity of Px times concentration of Px plus the molar absorptivity of P times P naught minus the molar absorptivity of P times the concentration of Px. Note here that epsilon P naught is A naught, which is the initial absorbance before any of our X has been added. And thus, the absorbance A is equal to the concentration of Px times the difference between the molar absorptivity of Px and P plus A naught, this initial absorbance before any X has been added. And now we can solve this for concentration of Px is equal to the change in absorbance divided by the change in molar absorptivity between P and Px. So again, that delta epsilon is the difference between the molar absorptivities of Px and P, and the delta A, that change in absorbance, is the absorbance that we have minus the initial absorbance without any X added. That is, that delta A is the absorbance after adding X minus the initial absorbance. And we can now combine these two equations together to give us the Scatcherd equation. So we have delta A divided by the concentration of X is equal to K, the equilibrium constant, times delta epsilon, the change in molar absorptivity, times P minus K times delta A. And now a graph of delta A divided by concentration of X versus delta A will be a line with a slope of minus K. Now if K is small, then we need the concentration of X to be large in order to produce Px. And this means that X naught is much larger than P naught, and the concentration of X is approximately X naught. If, however, K is not small, then the concentration of X is not equal to X naught. And thus the concentration of X has to be measured either at a different wavelength or via some other method. And that was measuring an equilibrium constant, the Scatchard plot.